Hello students. Today we are moving to next chapter, chapter number 7. It's a deadlock. Name of the chapter is Deadlock. So under today's lecture we are going to cover a basic about the deadlock problem. What is a deadlock problem? We'll try to understand what are the various characteristics for a deadlock to occur, or in other words it's a deadlock characterizations. And then we'll try to understand the resource allocation graph, which is basically a way with which we can understand whether there is a deadlock in a system or not. So to understand with the problem, I'd like to give you one example. Suppose there is a computer system. Suppose there is a computer system. So in a computer system, you may have many processes. Okay, so you may have many processes. So I just represent the processes with this circular thing. So name of the process is A. And let me give you another example. Do you have a similar kind of process in the same system? Name of the process is B. So like A and B, there may be many processes in a computer system that are executing their codes or the instruction in a multi-programming fashion. And during the execution of this process, so say for example, A is executing some certain set of instruction and B is also executing some certain set of instruction. So during this execution of this instruction by A and B processor respectively, so it may demand for resource, and in a computer system there may be many resources. Okay, so say for example, this resource is R1, and there may be many other resources of different types. Say for example, the another example of resource is R2. Okay? So some of the examples of resource R1 like could be your keyboard or your printer, okay, or another example could be a memory device. And sometimes the process A or B, a similar kind of process may request sometimes for printer or sometimes for memory, for reading and writing operations. So there may be n different kind of tasks that you can assume in a multi-programming system where there are multiple processes requesting or demanding for different resource to complete its task. So the sequence is that during the execution, the sequence is that suppose A have certain set of instruction, and somewhere in between the mid of the instruction, A has requested for a printer. Okay, so R1 is a printer, say for example. So first of all, what will happen is that process A will request for resource R1 because it needs to complete its task. Okay? But the R1 is busy with somebody else. Okay? R1 may be currently R1, the printer may be currently being used by the another process B. Okay? So printer is that kind of resource which cannot be shared, okay, at the same time, which cannot be shared at the same time. So if R1 is being used by process B, okay, if A is demanding, then R1 A has to wait for R1 to get released by process B so that R1 can be used by A, because R1 is busy currently. R1 is busy with process B. So this may be the sequence, right? So you may correlate the same thing with the real time scenario. Okay, suppose there is two student A and student B. Okay, and the teacher is dictating some notes, and it has to write it, or the students has to write it. But student A have only copy notebook where they can write it, and student B have only um, pen. Okay, it doesn't have student B does not have um, notebook. Okay, so each one of the student have one resource each, but to write whatever the teacher have dictated, A needs both resource R1 and R2. Okay, so you might end up with the situation like currently A have pen. Okay, currently A have pen, R2 is pen. So now to write it, it needs pen. Not only pen, it needs notebook also. So it is requesting for notebook, but notebook is assigned to uh, student B, and student B, in order to complete this task, it has requested for pen, right? So this is kind of a circular thing. You can see. I'll just repeat it. To complete the task of A and B both, for whatever the teacher have dictated, it needs to write it. They need both resources, that is pen and paper, right? So a process student A have got pen but does not have got paper, whereas student B has got paper, does not have pen. So what will happen is that the situation is something like A is holding a pen and requesting for a paper, and B is requesting for a pen and holding a paper. Okay? So you may enter this kind of situation where both the student cannot do the task. A also cannot do the task, B also cannot do. This situation is known as a deadlock situation. And same situation may happen in a computer system where there are multiple processes executing the instructions, and during the execution of the instruction, it may hold some resource and request some resource. So there, for example, so in a multi-programming system, so a process is holding a resource R2 and is requesting for R1 resource. Okay. Whereas process B is requesting for R2 and holding a resource R1. And to complete the execution of process A and B, okay, R1 and R2, both of them are not free at the same time. One is held, one is requesting. Okay? So each one of these allocated to different resources. So both A and B cannot do the task. So this situation is known as a deadlock situation. Okay, so we'll move back to the slide. So I'll just read it out. What is the problem? A set of block process, each holding a resource and waiting to acquire a resource held by another process in a set. Okay, this situation is known as a um, deadlock situation. So A also cannot execute because it has not got all resources that it has. It should be using it to complete its task, and similarly, that follows with the B as well. So it has both process will be in a deadlock state. Okay, this situation is known as a deadlock problem. Now, so we have seen the example of multi-programmed OS. We find that kind of problem in multi-programmed OS where multiple programs are executed with the help of the instructions. Okay, and these instructions sometimes required to complete the execution of the instruction. It requires some resources, right? Okay, so so this is an example you can see that may happen in a computer system. So a system has two tape drive. Okay, tape drive is the example of the tape drive is the example of the resource. So you can consider this R1 and R2 as a tape drive from 1 and tape drive 2. Okay, and there are two processes, P1 and P2, A and B. You can consider it holding one tape drive, and each need one another. So P1 is holding one tape drive and it is requesting for another tape drive. P2 is holding another tape drive and requesting for another tape drive. Okay, so now neither P1 can execute nor P can complete this task. Both of them will be in a wait and watch situations. So this situation is known as a deadlock problem. Yes. Okay. So we'll move back to the slide. So this is a data problem. Okay, if you try to, let us have a look on another example, real-time example. Suppose there is a breach. Okay, suppose there is a breach, and this highlighted that I'm hovering over this mouse. This is a two-way breach. Two-way breach means in one side the car will come in one direction, in another side the car will go in another direction. So this is also another two-way bridge. But in between these two bridges, there is a narrow bridge where only movement of one car is allowed. Okay, so suppose you enter a situation at a particular time that there is a car, okay, which has reached at this position, and there is another car from this direction which has reached at this location. Okay, now this car will expect this car to move back and vice versa. However, these expectations will lead to indefinite situations, indefinite time. And this car is expecting that this car will go back, and this car is expecting this car will go back. So this situation is known as a deadlock situation. Okay? So the traffic is only one way, only one car can enter at the same time. So either one of them has to release the resource, that is bridge. So you can consider this car as a process and the bridge as a resource. So this is known as a bridge crossing example. It's a real-time example. And if this situation is occurring for indefinite amount of time, then it leads to a starvation situation. Okay? It leads to a starvation situation, and the name of this situation is deadlock. Now, in a computer system, as I've talked already, that there may be many resources. Okay, there may be many resources. So the resources in this chapter we will be following certain standard notation. Each and every categories of resources, each and every categories of resources, we are representing it by a subscript R1. So R1 is one category of resource. Okay. R2 is another category of resource. Dot dot dot. RM is another category of resource. For example, suppose in a computer system there may be two printer attached with it. Okay, so we represent that resource by R1. So although there is two printer, but we will have follow the notation as R1. So R1 points to say for example R1 points to um, printer. Okay, now there is a mechanism for how to represent two printer. Okay, which will be discussed later on. Next is uh, so another examples of the resources could be CPU. Okay, CPU. So because CPU is also one of the resource. Another resource could be memory, and another example of resource could be IO devices like monitor, keyboard, mouse, etc. So these are the various different kinds and the categories of resources that is attached with the computer system. Uh, so whose notations are R1, R2, R3, in other words Ri. Okay, R subscript I. Okay. Now now uh, so Ri. Okay, Ri is the notation. Now in a computer system, as I've given you already example, in a computer there may be two printer. Okay, there may be two printer. For example, suppose there is a two printer. Okay. So I represent the resource of category of these resources as Ri. Okay. So this Ri or it may be Ri, may be 1, 2, 3, 4, anything. Okay. So this resource is of type printer. Now, if there are two printer, then we will represent it by instance. So small 2 square bracket. So here this notation that you can see over here, this Ri is a resource type which I have got two instance, two printer as attached with the system. So this is how we follow the notation. Okay. So Wi is the word that we are going to use for instance. Okay. Now whenever in a multi-program source, okay, where there are multiple different kind of resources attached with it, so the process which demands for some resource have to make the request first, because this is the format that the operating system will be using it in order to assign and allocate the resources to the requesting process. It has to first demand that I need printer or I need CPU cycle, and whenever it wants any kind of resources. Okay, and yeah, after making a request, now based on the availability of the resource, it may be granted. Okay, for example, suppose there is a resource. Suppose there is a resource I, I. Okay, I'm not worried about your sets, and there is a process P, I. Okay, now somewhere in between the execution of the instruction of by process Pi, it may require this resource Ri. So what it will do? It will make a request. So it will make a request. So now RI may be freely available or it may be allocated to some other process. Okay, based on that situation, if it is not available, so it may happen that RI is busy with some other process. So if this is situation, then PI has to wait for RI to get released. It cannot snatch it. Okay, so this is one situation. But it may happen that whenever it has requested, the RI is free. Okay, so if it is free, then it will RI is assigned to PI. So this is the format that you need to follow. So you need to request whenever you want to use any resource. Okay. Once operating system allocates the resource to the requesting process, the process is allowed to use the resource. Okay. After completing the task, it will voluntarily release it. Okay. Voluntarily release it so that it can be used by some other process. So this is one thing. Now what is the characterization? How do you know whether the situation, whether the system has entered into a deadlock situation or not? So I'll just roughly speak it out about the deadlock characterization. So for a deadlock to occur, okay, if somebody is saying that the computer system has entered the deadlock situation, then all these four criteria has to be satisfied at the same time. Okay, so for example, at time t equals to 1, okay, suppose at time t equals to 1, 10 a.m., okay, 10 a.m., this system has entered into deadlock situation. If somebody says that, then all these four conditions has to be satisfied. All these four conditions has to be satisfied. So what are those conditions? Mutual exclusion. First one is the mutual exclusion, means only one process at a time can use a resource. That is very, very obvious. So there may be different types of resources. So a resource can be used by only one process at a time. No sharing of resources. Okay. So for example, printer is a kind of mm, resource which does not share at all. It does not have a sharing feature at all. But memory it can be. Okay. But this is not the situation in this case. For a data to occur, the resources should be mutually exclusive. Okay. Resources, and for using the resources, it should be used in a mutual exclusive manner. Mutual exclusive manner means whenever any process is using it, nobody allow other process is allowed to use it. Okay, this is one thing. Next is hold and wait. Okay. Now, there should be, in a system, there should be a situation with the process that it is holding at least one resource and waiting to acquire another resource. Okay. For example, suppose if I say the system has entered into the deadlock situation, then you should have definitely this situation. Like suppose there is one resource R, okay, and there is a process P, okay, and there is another and there is another resource R. So there should be situation this, okay. The process should be at least holding one resource and requesting for another. So R is R2. Okay, R1 is allocated to R1 is held by the P1 and is requesting for R2. So this is the notation. So you should have this situation. At least there should be at least one at least process. There should be at least one process holding one resource and is waiting for some additional resource. Okay, and this additional resource R2. So P1 is requesting for R2, but R2 is busy with somebody else. Okay, so this situation should be there. This is our second criteria for a deadlock to occur. Next is the no preemption. I'll just read it out. No preemption means a resource can be released only voluntarily by a process holding it process after that process has completed its task. So means that whenever P1 is requesting for R2 and R2 is busy with P2, okay, then this R2 cannot be snatched from the P2 by process P1, okay, irrespective of priority or whatever it is. So R2 has to be released voluntarily by P2, then only it can be assigned to P1, a requesting process. So no preemption. No preemption means the P1 cannot preempt the execution or the uses of R2 by P2. So no preemption means that. Okay, a resource has to be a resource that is held by the some other process has to be released voluntarily. This is our third criteria for a deadlock to occur. Okay, and the last one is very easy. So you'll have a list of just hold it. So you'll have a list of process. Okay, P1, P2, P3, and number of process. Okay, I'll just write it out. So there are list of process P1, P2, P3. Okay, I'm only writing this much dot. There are n number of process. Okay. Okay, before this n there is Pn minus 1. So sequence is something like this, circular weight sequence something like this. P1 is holding a resource R0, holding is this symbol, okay, and is requesting for R1. Okay, is requesting for R1. But R1 is being held by the P2 and is requesting for R2. Okay, and the same sequence follows. R1 is sorry, R2 is being held by the process P3 and is requesting for uh, uh, R4, okay, or something like that, okay. And the last process Pn minus 1, okay, Pn, the resource n minus 1, the resource n minus 1 is being assigned to Pn, is requesting for R0. So this is kind of circular thing, okay. This is known as circular sequence. So there exists a set of process P0 running from P0 to Pn. This last characteristic Pn of waiting process such that P0 is waiting for resource that is held by P1 and so on, okay, the way that I have explained you. So for a deadlock to occur in a computer system, all these four criteria has to be satisfied. Then only we can say that deadlock has occurred. Okay? So this is one of the characteristics to understand whether deadlock has been occurred in the system or not. Now we'll try to understand resource allocation graph. This topic is something different. Okay, so because in this using this topic, what we are going to do out here is that we will look at the snapshot of the system, current view of the system. Snapshot means current view. We look at the current view of the system. Okay, then after that we'll try to draw a graph. Okay, we'll try to draw a graph. Then we'll try to analyze a graph, and after analyzing the graph we will say that, okay, we will say that the system is in a deadlock state or not. So this is one thing. So that's what we are going to cover in this topic, resource allocation graph. Okay, so we'll go on. Okay, so in a computer system there may be set of process. Okay, it has got certain way of representation and certain set of resource. Okay, and with different instances, it has got also certain way of representing it. Okay, we'll go through it. So first of all, let us think about the graph. So in a graph, okay, in a graph, what are there? In a graph there are vertices. In a graph there are vertices and edges. Okay, so vertices represents process. Okay, vertices represents process and resource. So process is represented by set Pi. Okay, P1, P2, P3, and resource is represented by character R. Okay, so Ri. So R1, R2, R3. As I've told you already that P1 means first process, P2 means another process, and so on. And R1 means one category of resource, R2 means another category of resource. It's not that R1 is printer, R2 printer. Okay, it's not that. If in a computer system there are two printers, then that is represented with the help of the instances. So Ri means a particular category of instances. Okay, so graph, in a graph we are going to use a graph, or we are going to draw a graph where we are going to use vertices, and there are two different kinds of vertices. One is P, which stands for process, and another is resource R. Okay, so in a graph we are going to, so while drawing a graph we are going to follow certain notation. So while drawing a graph we are going to follow certain notation. So a process of or the vertices of type process is represented by a circular, and a resource is represented by a square or rectangle. Okay, and if there is more than one instances, we are going to either draw a dot something or a small square on it. Okay, so this means there is this is a resource Ri. Okay, this is a resource Ri with two instances. Okay, and the process Pi. So this is the notation that we are going to follow, and this is known as a vertices. Okay. Now coming to the point A's. Okay, there are so the A's we are going to use in a graph is directed A's. So directed A's. So from where to where it is going. Suppose there are two different kind of age. Okay, one is requesting and another one is assigned. So as I've told you that whenever the process wants to use any resource, it has to make the request. Okay, based on the availability of the resource, operating system will assign it. Okay, so that request age will now become assignment. Okay, so I'll just give a rough view. Okay, suppose there is a process P and there is a resource R. Okay. Whenever P wants to use R1, it will make a request. So requesting A's direction will be from P to R. Okay. So this arrowhead, you need to understand, this arrowhead is a requesting A's. Okay. This is one thing. Now when this R1 is free, R1 is assigned to P. So this symbol. So this, looking at this directed A's from resource to process. Directed A's from resource to process is known as assignment age, and directed A's from process to resource is known as a requesting age. Okay, so directed requesting age and assignment age. Now, as I told you, process is represented by a circular thing. Okay, so this is what, and resource square. If there is four instance, four small or four dots will be sufficient. So pi requesting one instance of rj. Okay, so it is requesting, and pi is holding an instance of rj. So one instance of rj is being assigned to pi. Okay, one instance. So this arrowhead directed A should come from instance to process. Instance to process. Okay. So we'll move ahead. Suppose you consider a system. Suppose you consider a system P1, P2, P3. Okay. P1, P2, P3. And you need to interpret this. Okay. There are three processes P1, P2, P3, and there are four resources in the computer system: R1, R2, R3, and R4. The instance of R1 is, there's only one instance, so one dot. There is only one instance of R3, so that's why one dot. There are two instances of R2, that's why two dot, and there are three instances of R4. Okay, that's why three dot. At a particular time, say for example t equals to 10 a.m. or 12 a.m., whatever it is, at particular instance of time, a particular snapshot of the system, what is happening out here in this case, one instance of R2 is assigned to P1 and is requesting for R1 instance, but R1 resource is being allocated to P2. Okay. Now one instance of R2 is assigned to P2 and is requesting for R3. Okay. Then after that, one instance of R3 is assigned to process P3, and the resource R4 is not being used by any one of the process. Okay, so looking at this system, snapshot of the system, you need to tell whether the deadlock has, whether there is a, whether the system is in a deadlock state or not. So looking at this system, I can easily make it out that it is not in a deadlock situation. For example, once P3 completes its task, okay, it will release R3, and once R3 is released, it is assigned to P2. It will assign R3 will get assigned to P2. Now P3 is have completed its task. Now P2 has already R1 of one instance and R2 of one instance, and now R3 is also free. It has got all three instances to complete its task. So P2 will get all instance of R1, one instance of R1 that it is holding, one instance of R2 that it is also holding, and it has recently achieved R3. So P2 can execute all instruction with the help of this resource R1, R2, and R3. So P2, once it completes its all tasks, so P1 also get release of R1 and all. Okay, and that's how the task is completed by all three processes. Okay, so this system is not in a data set. Let us have a look on the another resource allocation graph where it enters the deadlock situation. Okay. So for example, this same number of instance, P1, P2, and P3. This scenario is something like this. Currently, one instance of R2 is assigned to P1. Okay. P1 is requesting for R1 resource, and the resource R1 is allocated to P2. Now P2 is holding one instance of R2 and is requesting for R3, and the R3 is being held by the P3, okay, and is requesting for R2. Now looking at the system, okay, looking at the system, so it's happening that P1 is expecting some other process to get resource released. Okay, wherever each of the process is having the thinking of same thing, that somebody will release the resource and I'm going to use it, but it's not going to happen. So this situation is known as a deadlock situation. Okay, so now how do you make a conclude that whether there is a deadlock in the system or not? Okay? So if a graph contains no cycle, no deadlock. Okay, so we'll see the first example. So can you see over here that is there any cycle? So arrowhead going from here to here, here to here, here to here, okay, here to here. There is no cycle. Okay, there is no cycle. So cycle means, what is a cycle? I'll just explain it. What is a cycle? Okay, so this is a cycle. So you can see this one. Yeah, this one is the cycle. Okay, see, arrow is coming from A to R1, R1 to B, B to R2, R2 to A. This is a cycle. You can see the directed edge. So however, if you don't see any kind of circular thing, a circular arrowhead, then no deadlock. Okay? Now you need to check out here whether there is a cycle or not. Okay, so from here to here there is one arrowhead. From here to P1 to R1 there is another arrowhead. From R1 to P2 another arrowhead. From P2 to R3 another arrowhead. From R3 to P3 and P3 to R2. So there is a cycle going from here to here. P1, P1 to R1, R1 to P2, P2 to R3, R3 to P3, and P3 to R2. Okay, so there is a cycle. So now if a graph contains a cycle, then there is a possibility that um, uh, there is a possibility of deadlock. Okay, if there is a possibility of deadlock. Now whenever there is a cycle in a resource allocation graph, then we can only assume that uh, it may happen a deadlock situation. Okay, so now I'll give you another scenario, so where you can definitely say there is a deadlock. Okay, suppose there is a resource R1, okay, and there is another resource R2, and there is a process P1 and there is another process P2. So there is only one instance of R1 and only one instance of R2. So R1 is being held by the process P1 and is requesting for R2, whereas R2 is whereas P2 is holding an instance of R2 and is requesting for R1. So now you can see there is a circular thing and there is only one instance of R1. So this is a definite deadlock situation. So let's move back to this slide. So if a graph contains a cycle and if only one instance per resource type, then deadlock. Okay. If there are several instances per resource type, then there is a possibility of deadlock. Okay. So here in this example, there is a possibility of deadlock. We cannot say and there is a deadlock. Okay. So you can see there is in this example there is a cycle. Okay. So P1 arrowhead going to R1, from R1 going to P3, from P3 going to R2, and R2 going to P1. So in this there is a cycle, but there is no deadlock, because once P2 complete its task, or once P2 complete its task, this resource will get released, which can be assigned to P1, and that's how we can break the cycle. Okay, so this is how you need to understand how to by looking at the graph, you need to tell whether there is a cycle or not. If there is no cycle, obviously no deadlock. If there is no cycle in a resource allocation graph, there is no deadlock. But if there is a cycle, then you need to check further. Okay, if the number of instances in each resources in a cycle, if only one instance per resource type, then definitely there is a deadlock. If there is multiple instances, then we can only say assume that it may happen that system may be in a deadlock. It's not guaranteed. Okay, so this is what facts you need to understand about the resource allocation graph. So we have seen some of the examples of how to represent the process and the resource with instances. We've seen example of resource allocation graph. Resource allocation graph with deadlock by checking at the cycle, or the possibility deadlock by checking at the cycle, and the criteria for a deadlock to occur and deadlock not to occur, and the possibility that they may have the system may be in a deadlock situations. Okay, okay, that's all for today. So if there is any questions, you can please post up. Okay, or you can have a discussion in the next session. Thank you so much.